Look up at the night sky. Each star is a sun, many with their own planets. We live on one such planet, teeming with life, all connected by a common ancestry stretching back billions of years. But how did life begin? How did non-living matter organize itself into something alive? This is the story of abiogenesis, the natural process that turned chemistry into biology. Life's origins aren't magic but the result of energy time and the laws of physics. Abiogenesis proposes that under the right conditions, simple molecules can become complex, eventually gaining metabolism, reproduction, and evolution. To understand this, we must travel back to a world before trees, dinosaurs, or even the first cell. For centuries, people believed in spontaneous generation, but science showed us life comes from life. Yet, if you trace life back far enough, you reach a time when there was no life at all. The puzzle. How did the first life get started? Today we use cosmology, geology, chemistry, and biology to piece together this story. What we've learned so far is breathtaking. It connects our existence to the formation of stars, the cooling of Earth, and the energy of its primordial environment. Maybe life isn't a rare accident, but a natural outcome of planetary evolution. This cosmic perspective puts our existence in a grander context. So let's begin our journey. Let's travel back 4 billion years to witness the birth of life on Earth. Imagine early Earth, no blue skies, no continents, just volcanic islands in a global ocean. The sky was thick with toxic gases, the air heavy with water vapor, methane, ammonia, and hydrogen. This was a chemical cauldron, a planet-sized laboratory for life's ingredients. The oceans were a hot, acidic, churning soup bombarded by meteorites and comets delivering water and organic compounds. Intense ultraviolet radiation and volcanic heat powered chemical reactions, breaking apart simple molecules and forming more complex ones. This deadly environment was perfect for the chemistry of life to begin. The right ingredients and powerful energy sources were all present. The planet was a vast chemical reactor, bubbling with potential. All that was needed was time, millions of years for the first act of life's drama to unfold. The stage was set for something extraordinary. How do we test what happened 4 billion years ago? By recreating early Earth in the lab. In 1952, Stanley Miller and Harold Urey did just that. They built a closed system with water to mimic the ocean and gases like methane, ammonia, and hydrogen for the atmosphere. They added sparks to simulate lightning, providing energy for chemical reactions. The cycle of evaporation, electrification, and condensation ran for a week. The result? The water turned from clear to deep red-brown. Analysis revealed complex organic molecules including amino acids, the building blocks of proteins. This experiment proved that life's building blocks could form naturally from simple chemistry. It showed that the transition from non-life to life's ingredients was not a miracle, but a likely outcome of early Earth's conditions. The Miller-Urey experiment was a turning point, showing that the chemistry of life is within reach of nature. It inspired generations of scientists to explore how life could emerge from the elements. The experiment didn't create life, but it showed the first steps are possible. It brought us closer to understanding our own origins. The story of life's beginning was no longer just speculation, it was testable science, and it all started with a spark. The Miller-Urey experiment supported the idea of a primordial soup, Earth's early oceans rich with organic molecules. For millions of years, lightning, volcanic heat, and sunlight created ever more complex mixtures. Amino acids and nucleotides, the building blocks of proteins and genetic material, formed in this global chemical factory. Tidal pools and hydrothermal vents provided microenvironments where molecules could concentrate and react. In these places, amino acids linked into peptides and nucleotides formed strands of RNA. The primordial soup was dynamic, with increasing complexity driven by Earth's energy. Hydrothermal vents, rich in minerals and energy, may have been the true cradles of life. Whether in sunlit pools or deep-sea vents, simple molecules began to self-organize. This was a gradual process, not a single event, complexity building over time. The soup was simmering and something new was about to emerge. The building blocks of life needed organization, a way to separate from the outside world. Lipid molecules naturally formed bubbles or protocells, creating tiny compartments. These protocells trapped different molecules, creating miniature laboratories for chemical reactions. Some protocells may have captured self-replicating RNA, marking the dawn of heredity and evolution. The RNA world hypothesis suggests RNA was the first genetic material, able to store information and catalyze reactions. Protocells with self-replicating RNA could reproduce and pass on traits, allowing natural selection to begin. Over generations, protocells became more complex, developing better membranes and more efficient replication. Eventually, DNA took over information storage, and proteins became the main catalysts. The protocell crossed the threshold. It was now a living cell. This was the last universal common ancestor, from which all life descends. From simple chemistry, individuality and evolution emerged. Life had begun. Abiogenesis on Earth inspires us to search for life elsewhere. If life arose here, why not on other worlds? We explore moons like Europa and Enceladus, with subsurface oceans and possible hydrothermal vents. We search for exoplanets with water, energy, and organic molecules. Amino acids found in meteorites show life's ingredients are common in space. Abiogenesis suggests life could be a natural outcome of planetary chemistry. Every discovery, new exoplanets, complex molecules, adds to the puzzle. The quest to understand life's origins connects us to the cosmos. From stardust to thinking beings, that is the journey of life.